Okay, so we'll continue with our previous class discussion about the resource allocation graph RAG. There we have discussed that in a resource allocation graph, the processes or the resources can become the vertex. Like you can see over here, these are the P1, P2, P3 are the processes, R1, R2, R3, R4 are the vertices, are the resources, and these becomes vertices. And these dots indicates that how many resources of this particular type is available. It means that two resources of resource type R2 is available, three number of R4 resources are available. If there is a process from, if there is an edge from process to resource, that means process is requesting for the resource. If there is an edge from resource to process, the resource is allocated to that process. Correct? We say this is assignment edge, and this we say as the request edge. P1 is requesting R1, so it is a request edge. R1 is assigned to P2, it is assigned edge. And if the resource allocation graph contains a cycle, then we may say it may be in deadlock. So here we can say it is in deadlock because you can see this is this this is not in deadlock because there is no cycle over here. If there is no cycle, it is not in deadlock. This is not in deadlock. Let us take another example. We have same three number of processes and four types of resources R1, R2, R3, R4. Same two number of R2 and three number of R4 are there. Now we have something, the request is and the assignment is something like this. Whether it is in deadlock or not. Whether it is in deadlock or not. Look into this graph and say whether it is in deadlock or not.
Yes, sir.
So why you say it is in deadlock?
Because it forms cycles from R2, then it again return to R2.
Okay. So it forms a cycle like from P1 to R1, P2, R3, P3, R2, P1. So it forms a cycle. There is another cycle P2, R3, P3, R2 and P2. So there are two different cycles over here. The processes involved in a cycle are said to be in maybe in the deadlock. Those processes are in deadlock. There may be n number of processes might be running. Only the processes which are involved in that cycle are said to be in the involved in deadlock only. Now look here, we say this is in deadlock because looking into this graph. But can you tell me whether the third graph is in deadlock or not? Look into this and say whether it is in deadlock or not. Look into this third graph. P1, P2, P3, P4, four resources and only four processes, and R1, R2 are two resources. Two number of R1 and two number of R2 are there. Whether it is in deadlock or not.
So if we consider P1, R2, P1, R1, P2, then it is not in deadlock. But if we consider R2, P1, P3, R2, then it may be in deadlock.
It says that if you have a cycle in a graph, then it may lead to deadlock. So look over here, cycle is there or not? P1 to R1, R1 to P3, P3 to R2, R2 to P1. Is it a cycle or not? Yes, it is a cycle, but this is not in deadlock. So I will tell that why it is not in deadlock. Because you see over here, although it is a cycle, one of the resource of R1 is given to P2. So P2 is not waiting for other resources. So as P2 is not waiting for other resources, P2 will definitely finish. When P2 will finish, it will return this resource. And in the similar way, P4 is executing without waiting for other resources. So definitely P4 will finish because it is not waiting for other resources. So as it is not waiting for other resources, definitely it will return this. And once these resources are available, so P1 can get this resource because there is another additional resources over there. But in the previous case, it was not there. In the previous case, you can think, just think over here. Suppose I will take this cycle. This cycle. P1 cannot finish because P1 in the cycle. None of these processes can finish because they are P2 and P4. P2 and P4, they are not the part of this cycle. And they are not waiting for other processes, other resources to finish. Therefore, P2 and P4 will definitely finish and they will return their resources. Once the resource is returned, the previous processes which are waiting for that resource can start its execution. Is it understood or any doubt? Is it understood or anyone having doubt?
P1 and P3 are waiting for P2 and P4 so that P2 and P4 can finish their execution and can return.
Yes. Yes, very good. So P2 and P4 will definitely, the thing is that P2 and P4 are not in this cycle. So they will be definitely returning, they will definitely finish, and they will, once they finish, the resource will be revoked and the resources they will return. And now the deadlock can break. So what we will get from here? What is the conclusion? Conclusion is that if the resource allocation graph contains no cycle, then definitely it is not in deadlock. Correct? If it contains no cycle, it is not in deadlock. If it contains a cycle, then it may be in deadlock. It may be in deadlock. We cannot give a guarantee that it is in deadlock. Correct? If there is only one instances are there, only one instances are there, and there is a cycle. Do remember, if there is only one instance for each resource and there is a cycle, then it is in deadlock. Just think of, if I would have only one instance over here and here also one instance, then definitely it is in deadlock. Correct? So if every resource has one instance and there is a cycle, then it is in deadlock. So a cycle doesn't mean that it is confirmed by a deadlock. Deadlock may, there is only one resource and there is a cycle, then definitely it is in deadlock. Is it understood or anyone having doubt? Three conclusions we get. No cycle, no deadlock. First conclusion. Second, if there is a cycle, deadlock may exist. Third is that if there is only one resource of each type and a cycle, then definitely it is in deadlock. Is that understood or anyone having doubt over here? Okay. So see, if resource allocation graph contains no cycles, then there is no deadlock. No cycle, no deadlock. So cycle is always a necessary condition for deadlock. Therefore, if there is no cycle, then definitely there is no deadlock. We have already read the condition. What is the necessary condition for deadlock? Mutual exclusion, hold and wait, no preemption, and circular wait. So as the circular wait is not there, so no deadlock. So no cycle, no deadlock. First one. Second, if it contains a cycle, then also we do not give a guarantee that it's in deadlock. If only one instance per resource type, then it is in deadlock. If several instances per resource type, then possibility of deadlock. There might be deadlock may occur. There might be a deadlock over there. So these are our observations from the resource allocation graph. Okay. Now question is that how to handle the deadlock? How to handle the, if deadlock may occur, we know that there are many situations where the deadlock may occur. Now question is that how to handle the deadlock? Once deadlock occur, we have to handle the deadlock. So we will handle the deadlock in the following ways. In any one of these ways, we will handle it. What will you do? We'll try to prevent the deadlock. We'll try to prevent the deadlock. Prevention means we'll take some prevention so that deadlock will not occur. Suppose there is a prevention, some for a particular disease, for measles or for some, for some cold diseases, people take prevention medicines over there, so that this will not have, the cold will not catch me. It's a prevention. So before the deadlock, we'll take some prevention so that deadlock will not occur. Now we'll say that how to take prevention. We know that there are 4 necessary conditions for deadlock: mutual exclusion, hold and wait, no preemption, circular wait. And we have said if all these 4 will occur, then only the deadlock will occur. If all these 4 will occur, then only the deadlock will occur. Now what we'll do in the prevention, we'll try to prevent any one of them not to occur. We'll try that mutual exclusion should not occur, or the hold and wait will not be there, or no preemption will be there, or how to break the circular wait. If we could able to break any one of these, then the deadlock can be broken. So ensure that at least one of the condition cannot hold. That is the prevention of the deadlock. Correct? So we'll take measure that we'll take some preventions so that deadlock will not occur. So deadlock prevention is taken prior to the deadlock. It's like, you take a preventive medicine before the event occurs, or before the disease. You take a preventive medicine for the same. Next one is avoid the deadlock. Prevention and avoidance is 2 different things. The avoidance says that we must allocate the resources just before allocating the resource to the process. We will ensure that by allocating this resource, this will not lead to deadlock. If you could able to know, then either we will allocate the resource or we will not allocate the resource. Try to understand. Avoidance says that every process is requesting some resource. So avoidance says that whenever we are allocating some resource, before allocation, just before allocation, we'll check that by allocating this resource, whether it will lead to deadlock or not. Right? So we'll try to, try to avoid the deadlock, not by putting it in a risk state. Is it understood what I am saying? So if I know that in this road there is a heavy traffic, if I able to know, I could able to know, I will just at the last moment I can change my route. It is avoidance. Prevention, if I am riding a bicycle, I will wear the helmet, I will wear, or I will take on my prevention, then only I can go for the ride. So the avoiding the deadlock, the operating system needs some advanced additional information about which resources a process will request and use during its runtime. So during the runtime, how much resources the process needs and for how much time. That information we should have. And using this information, the operating system decides for each request whether or not the process should wait. So whenever a process enters a system, we'll see that how much resources it requires, which type of resource or how many it requires. So by looking into that only, we'll take a decision that whether it will be granted or not. This is known as avoidance, deadlock avoidance. So just before allocating the resource, a check is made whether it is in safe state or not. The prevention of deadlock says will take measure so that any one of these four conditions, necessary conditions, should not hold. Is that understood, the prevention and avoidance? Deadlock avoidance and prevention. If these two are understood, we have different measures. We'll read those. What are the different measures for preventing the deadlock and avoiding the deadlock? Okay, suppose we have taken all preventions. We tried to avoid the deadlock, but still the deadlock occur. So if a deadlock occur, we'll try to find out which of the processes are there in the deadlock. Correct? Like there might be n number of processes are there. Out of these n number of processes, some processes, few processes may be forming a cycle. So those are in the deadlock. So examine the state of the system to know whether deadlock occurred or not. To check that whether deadlock occurred or not, so we have to detect the deadlock. Correct? We have taken prevention. We tried to avoid the deadlock. If a deadlock occurs, we detect the deadlock and will recover from the deadlock. So after deadlock is detected, the operating system should have some algorithm to recover from the deadlock. We'll go for that, what to detect and how to recover. Correct? Now just think of, we have taken all preventions, we tried to avoid, we detect it, we tried to recover, still the deadlock occurs. What to do now? The doctor said that you are having, a person is having diabetes or sugar, you don't eat Kerala, you don't eat this, you go for walking, you go for medicines, you go for everything. He abide by everything, but still the diabetes is there. Then what to do? Then ignore it. Because we have taken prevention, we have taken avoidance, we have, whenever it occurs, we detect and try to recover, but still it is there. So sometimes we have to ignore the deadlock. So this means that all deadlocks cannot be resolved. So you have to ignore the deadlock, ignore the problem and pretend, means you ignore the problem and pretend that deadlock will never occur in the system. Just is a belief that you deadlock will not occur, you start working. So if it is a problem, you just have to ignore it, nothing more you can do. So last point says that in spite of all this, we cannot give a guarantee that deadlock will never occur. That we cannot give a guarantee. Is it understood or anyone having doubt? Deadlock handling mechanisms, all these 5: prevention, avoidance, deadlock detect, recover and ignore. Is it understood? Okay. Coming to the first one, we have said that these things we have to do. So first we'll go for the prevention of the deadlock prevention. So first one will go for deadlock prevention. What we have said in deadlock prevention? Deadlock prevention says that you should take some measure so that any one of the condition should not hold. Because the necessary condition for deadlock are mutual exclusion, hold and wait, circular wait and no prevention. So out of these four, if any one of these could not occur, then the deadlock can be break. So we'll see that how any one of these can be prevented. What prevention we can take. The first one is mutual exclusion. The first one is mutual exclusion. So how to prevent the mutual exclusion? It says that nobody can claim the exclusive user of the resource. If we will make a rule that you cannot have a exclusive access to a resource, you have to share it. Understood? If a particular, suppose memory is there, I'll say 2 processes has to share or 3 processes has to share the memory. You cannot have a exclusive access. Correct? If you make a rule that you cannot have exclusive access to a resource, right? You have to make it free, means you that can be shared. Then the mutual exclusion can be hold the mutual exclusion rule that we have to fixed for the first one can be avoided, can be handled. Correct? If you recall those examples, all those examples that we have given for deadlock, then the now mutual exclusion will convert to shareable. So they don't have any mutual exclusion, rather they can share the resource. If they will share the resource, then definitely deadlock will not occur. So mutual exclusion is implemented only on non-shareable resources, but difficult to implement. If the resources are non-shareable, for example, memory is shareable, hard disk is shareable, but some resources are non-shareable, like printer, for example. Printer is non-shareable. How could 2 people can share a printer at the same time? Suppose 2 people are sharing the printer, is it possible that a page will come out with half of the printout of your document and half of the printout of another document? They have to access it exclusively. The printer will take one document, then it will take the document of the another, one at a time. So in that case, it is non-shareable. It is non-shareable. Correct? So, but some resources are there which are shareable. Memory can be shared. A hard disk at a particular moment, 2 users can have shared to the same hard disk. Correct? So, some of the resources are shareable and some of the resources are non-shareable. The resources which are non-shareable, they cannot go for mutual exclusion. Therefore, we cannot convert all non-shareable resource to a shareable resource. What is the rule for mutual exclusion? What is the rule for preventing the mutual exclusion? Convert all non-shareable resource to the shareable resource. Convert all non-shareable resources to the shareable resources. But what is the problem? Problem is that all non-shareable resources cannot be converted to shareable. Example is printer. Anybody having doubt on the mutual exclusion? First you say, so that we will go for the next one. Any doubt? Hello? Is the mutual exclusion prevention is understood, or anyone having doubt over here? Hello? Is it understood?
Yes, sir.
Yes, sir.
So next one is hold and wait. How to prevent the hold and wait? The hold and wait says, this is the second necessary condition for deadlock. And what is hold and wait? Hold and wait said, when a process is holding some resource and waiting for additional resource. When a process is holding some of the resource and waiting for another resource, and then it causes the deadlock. It must release the resource and then it may request for additional resources. So it is not releasing. So what we should do? The rule it says that first of all, it must guarantee that whenever a process requests a resource, it doesn't hold any other resource. We will make a rule that whenever a process will make a request of a resource, it doesn't hold any other resource. So it has to release all the resources before making a request. Correct? Another way of saying that a process can only start its execution whenever all its resources are available. If all resources are available, it will start execution. If not available, it is just in waiting state. Otherwise, what happens? If some of the resources are available, while availing it, some it is not getting, so it comes under the hold and wait. So it can be implemented in two different ways. Each process requests all its resources at the beginning, and it starts executing when it get all its resources. So that means a process can start its execution when all its resources are available. If it is not available, it will not start. It will not start with some minimum number of resources. Another way is that a process may request some additional resources, use them before it can request additional resources, but it must release all the resources it is currently allocated. First one, what to avoid the hold and wait, what it says, will make a rule that whenever a process will start, it must acquire all the resource, then only it will start. Second one is that it may get half of the resource and it will start execution. But when it is requesting for additional resource, it has to release all its previous resources. If any one of these will be implemented, then the hold and wait condition can be avoided, can be prevented. The hold and wait condition can be prevented. But there is some problem. If you implement any one of these, the resource utilization will be very low and there might be a starvation, because somebody will, before starting, will take all the resources until its execution, till it has not finished the execution, it is not releasing the resource. So other processes are just waiting over there. So other processes may be in starvation, right? Or if it is half of is executing and requesting for additional resource, and it is it has to release the previous resources, but there might be a dependency for which it cannot continue the execution. So therefore resource utilization will be very low and there may be starvation. Correct? So this is to prevent the hold and wait. So two rules we have applied over here. This is the first rule and this is the second rule, that is for the hold and actually the meaning is same. Whenever a process starts this execution, if it has all the resources, it can start, otherwise not. Second one, it may start with some minimal resources, but whenever it is requesting for additional, it has to release all its previous resources. Okay. Next one is no preemption. We have said by ensuring at least one of these conditions cannot hold, we can prevent the occurrence, correct? So next one is how to prevent the no preemption. How to prevent the no preemption. So before going to this, let me explain you. Suppose this is the process is requesting some resource. Suppose this is the process P1 is making some request. That resource is held by P2. That resource is held by P2. Try to understand. P1 is making a request. The resource is held by P2. P2 is currently using it. If P2 is also waiting for other resources, if P2 is waiting for other resources, correct? Then which will finish and give, then the P1 has to wait. If P2 is waiting for a resource which is held by some other process, then the currently holding resources has to be preempted and given to P1. Try to understand. P1 is requesting some of the resource which is currently held by P2. Now either P2 is using some of the resources, suppose P2 is requesting for some of the resources and these resources are free, then definitely P2 will finish. So at that case, P1 has to wait. Suppose P2 is also waiting for the resources which is held by P3. In that case, the currently holding resources, what is there at the P2, can be given to P1 so that P1 can start its execution. Is that understood? Is it understood?
Yes, sir.
P1 is requesting some resource. P1, those resources are held by P2. And along with these resources, P2 is requesting for additional resources. So either these additional resources may be free or this may be held by some other process. If it is free, then P1 has to wait. P1 will be going to waiting state because P2 will definitely finish and P1 will get. But if they are also held by another process, P3, then the currently holding process resources by P2 are given to P1 so that P1 can continue its execution. So we can preempt those resources from P2 and give it to P1. Okay. So this is the way the preemption can be avoided. So here it says all resources can be taken forcibly. What we can do in preemption? One thing we can do, we can preempt all resources forcibly. If something is there, suppose in a traffic jam is there and none of the vehicle is willing to move, then traffic police will come and forcibly will take one car out, or for some of the all processes out, all cars out. So all resources can be taken forcibly. If a process that is holding some resources requests another resource that cannot be immediately allocated to it, then all resources currently being held are released. So it has to release all the resources. Preempt resources are added to the list of resources for which the process is waiting. So if the resources are being preempted, those will be added to the list of resources. Those are for waiting. Process will be restarted only when it can regain its old resources, as well as the new ones that is requesting. That means those resources which are being preempted from here, this will be given to the old process, and along with its old resource and this resource, it can start its execution. In case of serially usable or non-shareable resources like memory space, CPU register, it can be used. But in case of non-serially or shareable resources, a printer, it cannot be implemented. So here it says, although deadlock prevention is works in some of the cases, but there are many cases where the deadlock prevention fails, particularly in the shareable. Particularly in the non-shareable, it fails. Correct? So we have read that how to prevent deadlock by using mutual exclusion, how to prevent deadlock by hold and wait, how to prevent from no preemption. So what is left now? We have left with circular wait. So how to prevent the circular wait? It says that there are some resources. So what we will do, for every resource, we will assign a number, integer number. So there is a function from resource to a natural number. So we'll have a function which is from the resource to a number n. That means resource hard disk, suppose 2, memory 3, printer 5, like that. So a resource having assigned with a number, that number we can think of as a priority, or any priority value that is being assigned with each of the resources. We will assign a value to each of the resources over here. Is it understood? We will assign a priority value to each of the resources. Then what we'll do? Then what we'll do, while allocating the resources to the processes, we'll follow a rule that if suppose initially, look over here, impose a total ordering of all resource types and request that each process request resource in an increasing order of enumeration. So what we'll do, we'll ensure that they will request in increasing order of enumeration. Suppose I have hard disk, then I may request for vector processor, or I may request for printer. Because hard disk priority is 2, I can request for printer, which is 5. But if I have printer, I cannot, sorry, if I have printer, I cannot ask for the punch card. So initially, a process can request instance of any resource type Ri. So initially, it will have Ri. Suppose I have hard disk, correct? After that, process can request instances of type Rj. Suppose it requests, now I have hard disk, I am requesting for vector processor. So it says that if this value is greater than this value, then only it will be granted. So if I have lower priority, I am requesting for a higher priority resource, it will be granted. But if I have a higher priority, I am requesting for lower priority, then it should not be granted. Correct? So whenever a process requests an instance of resource type Rj and it has released any resource Ri, so that priority of Rj, Ri and greater than equals to priority of Rj. So here you have alternative for I have taken. Here I have taken Rj and here I have taken Ri. Correct? So the above protocol guarantees that a circular condition cannot hold. How will you ensure that circular condition will not hold? How it ensures that circular condition will not hold if you go on allocating in this way, priority allocations? See over here. Suppose the the f of R1, if I take R1, when the first process allocates, this should be less than the R2, because the priority has to be less so that it can allocate, right? If the first process allocates something, it is requesting the second one, it can request for the next one if it has higher priority resource. If it will go on allocating in this way, suppose this is f of n-1. After n-1, what it will come? Again R1 will come. So that means, is it possible that f of R1 is less than also f of R1? This is a contradiction. So if you will go on allocating the resources on this basis, definitely will guarantee that circular wait will not occur or cannot hold. Circular wait cannot hold in if you go in this way, because always we are allocating the resource when it has a higher priority. So f of R1 less than f of R2, f of R2 less than f of R3, like that f of n-1 is less than f of R1, which is never true, which will never become true. So therefore, the circular wait cannot occur. Correct? So we have taken all preventions for, so that any one of these 4 should not occur. Any doubt on from the deadlock prevention? We have read about the deadlock prevention for how to avoid all these four necessary conditions. Any doubt from these four? No doubt. Okay. We'll go for deadlock avoidance. As I told, in deadlock prevention, we take some measure before the deadlock so that any one of these conditions should not occur. But deadlock avoidance says that before allocating the resource, we must ensure that by allocating the resource, the system should not become unsafe. What is safe and unsafe? I will tell. So it should not lead to deadlock actually. So there are some side effects of deadlock prevention. As you have seen that there is a low device utilization, reduced system throughput. Because you can see in the hold and wait or no prevention, the device utilization is less, right? System throughput is less. So it requires that the system has some additional a priori information available about how resources are going to be requested. So you must have some information beforehand, before execution of a process. That means whenever a process will enter into the system, it will declare that I need these resources of how many types of resources and how many number of resources. I need 2 hard disks, 500 MB of RAM, 1 bus, 2 pen drives, whatever it is requiring, those information it will give, and for how much time. So it will give what whenever resource enters, it will give what is its maximum need. What is its maximum need, that it has to say, right? So requires that the system has some additional a priori informations. That means some informations we should know beforehand. Correct? So a priori informations available, and how resources are going to be requested. What is the order in which they are going to request these resources? So at least we must know what is the maximum need of resources for a particular process. The simplest and most useful model requires that each process declare the maximum number of resources for each type that it may need. The simplest and most useful model requires that each process declares the maximum number of resources of each type that it may need. Whenever a process enters, it will say that, for example, it will say that I need 2 hard disks, 500 MB of RAM, 2 bus, CPU, whatever the things it requires, all these it will say this type of resources and this number of resources. What is the maximum number of resources? It will say before execution. Correct? The deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that there can never be a circular wait condition. So there will be a deadlock avoidance algorithm. We will discuss that. There is a deadlock avoidance algorithm. It dynamically examines, means whenever there is a case to allocate some resource, the algorithm runs and ensures that if I allocate this resource to this process, the circular wait will not occur. And we know that if circular wait will not occur, then deadlock will not occur. So if before allocating any resource, we will check that it should not lead to deadlock state. Right? So that is, we say, as a deadlock avoidance algorithm. So resource allocation state is defined by the number of available and allocated resources and the maximum demand of the processes. If I say resource allocation state, what does it mean? Resource allocation state means there are three things. What is the number of available resources? What is the number of allocated resources? What is the maximum demand? Correct? Suppose a process will come, process P1 came. It will say that I need 5 number of hard disks, 3 number of bus, and say 1 number of CPU. Correct? It will declare before execution. This is P1 has declared this. This is the maximum demand. That means the process cannot demand more than this. It will declare it before execution. Correct? Now, out of this, some will be allocated. Suppose I have allocated 2 over here, two hard disks, and 1 I have allocated and none. I don't. So I will allocate something like this. So this is allocation. This is the maximum need. Correct? And the rest is your available. So before entering the system, the process must declare that how many types of resources or how many number of resources are required, that has to be declared. And some will be allocated to that. All these information has to be kept in a table. Correct? So next class we are going to solve a problem on deadlock. Actually, deadlock avoidance problem is called the banker's algorithm. We'll go for solving that. So this is all for the today's class. If you have any doubt, you may ask me now. In the meantime, let me take the roll attendance. If you have any doubt, you ask me now.